we can see if it's working. And we'll wait a couple of minutes if possible. Nice. Okay. ¿Dónde te estás emitiendo tú, Santi?
Sí, se están emitiendo solos, ya no
vale,
hay
vale. Vamos a dar un minuto de cortesía.
Vale.
Y luego la gente se conecta mucho por el canal de YouTube también. Por eso hay mucha gente aquí. Okay, let's start. Are you ready, Francesca?
Yep, ready.
So, well, welcome everyone. It's a pleasure for me to introduce you to Francesca Fragkoudi. Oh, it's Fragkoudi or Fragkoudi? Where you put the accent? I mean, it's Fragkoudi or Fragkoudi?
Fragkoudi.
Fragkoudi.
It's okay.
Okay, sorry. I mean, it's even in your presentation. Sorry. Fragkoudi. Yeah. Well, Francesca, I'm gonna do a little bit of bio. She did her PhD in Marshall, no, at the Observatoire of Astrophysique, with Liadana Saula and Albert Bosman. After that, he took a postdoc with Paola Di Matteo and Haywood, no, Michel Haywood, at the GEPI in Paris. Then she moved to Germany, to Garching, and he joined the Max Planck Institute for Astrophysics, where he worked in the group of Simon White and Walter Springer. And recently, he got an ESO fellowship, and he's working at the European Southern Observatory. Francesca has been doing a lot of work to understand the dynamics of galaxies, using both isolated and cosmological simulations, which is very good, because I don't know, I remember a few years ago that there were the people who were studying the dynamics in galaxies and they were only using isolated numerical simulations with static halos and very idealized gas accretion and things like that. So now the new generations, like Francesca and Santi as well, are joining the two fields, which is will allow to understand much better how galaxies as our Milky Way form. Well, I don't know what else to say. I could say a lot of things. She's also very interested in observations. Proof of this is that now she joined the European Southern Observatory, but also that she's part of big collaborations that are based on large programs of ISO, like Timer, where I don't know, I met you before, we were both in Timer, but we are both part of that collaboration. And I recently got an email asking to accept you as part of the funds collaboration as well. So I think you'll be part of it soon. And so that proves that she's not only interested in the simulations per se, but in understand the simulations and how to compare with the observations. So I think I'll stop here and I'll let you tell us what you have to tell us today.
Thanks, Patri. Thanks for the nice introduction. And yes, I am, a theorist that's infiltrating into the observation world also. So yeah, like Patri said, today I'm going to be telling you a little bit about some of the work we've been doing in using cosmological simulations, but not only cosmological, also isolated, to understand barred galaxies in the full ΛCDM context. And I'm going to be focusing on two main topics today. One is on the formation history of our Milky Way, so how we use these simulations to understand how our galaxy formed. And the other is on using these simulations to try and understand more about the dark matter content of Milky Way-type galaxies in general. So this is the outline of my talk for today. So I was told that there's a broad range of backgrounds who attend these talks. So I'm going to start with a very general and very broad overview on barred galaxies to get everyone on the same page. And then I'm going to tell you a bit about what we've learned about how our galaxy is formed and also about how much dark matter is in barred Milky Way-like galaxies. Okay, so I'm sure you've all seen this kind of diagram before. This is, of course, the Hubble classification, where Hubble classified galaxies according to their morphology, putting ellipticals over here on the left and spirals over here on the right. And of course, any theory of galaxy formation evolution, one of the main things that we want to do with this is to try and understand how we come up with this kind of diversity of morphologies in galaxies. So I'm going to be focusing today mostly on these galaxies down here, which are the barred spiral galaxies. So these are called barred spiral galaxies because if you look closely, you see that they have this elongated stellar structure that goes through the center of the galaxy, and this is called the bar. One thing that's really interesting about these barred galaxies is that they actually make up a very significant fraction of the population of spiral galaxies at low redshift. So we know that about 2/3 of disk galaxies in the local universe have bars. And you might have noticed I also snuck in here a picture of the Milky Way made with Gaia DR2 data, because we also know that our own Milky Way is a barred spiral galaxy as well. And one of the reasons why bars are so prevalent is that in galaxies is that they are able to redistribute angular momentum from the inner disk to the outer disk into the dark matter halo. And so they can bring the galaxy into a lower energy configuration state. And so when a galaxy can form a bar, it will form a bar. The other thing that makes these galaxies very interesting to study, and bars in particular, is that bars significantly affect their host galaxy. And they do this by redistributing both stars and gas in the disk. So for example, bars can induce shocks in the gas, and these create these dust lanes that you can see here. And these shocks cause the gas to lose angular momentum and to funnel towards the inner regions of galaxies. And there, this gas piles up, becomes very dense, and you can have intense bursts of star formation and feedback, and the formation of nuclear structures such as rings and nuclear disks and so on. And also this gas funneling to the center is one of the main contributors to the gas reservoir that feeds the supermassive black holes that are in the centers of massive galaxies, especially at late times. So at late times, you don't have other mechanisms in order to induce torque and to bring the gas to the center, such as mergers. And so bars are one of the main ways of really providing this fuel reservoir to the central regions. And like I said, the other thing that bars do is that they also, through resonances, can redistribute stars, both in the outer disk, but also in the inner Milky Way, in the inner disk of the galaxy, and they can form structures such as these so-called boxy peanut bulges. So I'm going to be talking quite a bit about boxy peanut bulges. So I want to talk a little bit first about resonances, just to get everyone on the same page. So on the left here, what I'm going to be showing you is a video of a simulated barred galaxy. This is from a cosmological simulation. And you'll see I've selected 3 stars, and I'm going to be tracing out their orbits. And so here, what I'm showing you are these orbits of these 3 stars in an inertial frame of reference. And these are stars that are on resonant orbits. And what you can see already just from looking at the orbits of these stars in the inertial frame is that the orbits are quite elongated. So they're not, totally circular. And now if we go and look at these same 3 orbits, but now in a rotated frame of reference, which is rotating at the same angular speed as the bar, we see that these orbits now appear to be almost closed in shape. So they're almost closed orbits. And you can see that, for example, in for this orbit here, this orbit is one of the bar supporting orbits. So this is what stars are doing in the bar region. They're moving up and down inside the bar. And these 2 orbits are orbits that are trapped at corotation, at the corotation resonance of the bar. And I'll talk a little bit about the corotation resonance in the last part of the talk as well. So what is happening to these resonant orbits? The reason that these stars are trapped in resonant orbits is because the frequency with which these stars move around the galaxy, which is given by the azimuthal frequency here, and the frequency with which they move in and out radially, are commensurate with the angular frequency of the bar. And so when this happens, you can think of this as, kind of a forced harmonic oscillator type situation, where you increase essentially the elongation of the orbits. And so these become very elongated. Now, the same thing, what I was just showing you are orbits that you can see that they're in resonance, let's say in the plane of the galaxy. But stars also, of course, as they move around the galaxy, they also oscillate up and down in the vertical direction. And if they oscillate with the right kind of frequency that's commensurate with the bar, then these orbits will become also vertically resonant. And when they become vertically resonant, the orbits are going to be distorted out of the plane of the disk, and they go into so-called banana or pretzel-shaped orbits, depending on the orbital family. And this is what gives rise to this peanut shape that we see in barred galaxies, and gives rise to this boxy peanut structure. And here, what I'm showing you now is going to be a video of an orbit, again, taken from one of these simulations. But now I'm showing this in the XZ plane, so that the galaxy is edge on. And this is an orbit that's going to get trapped in one of these vertical bar resonances. So what you see is that in the beginning, the star is confined close to the plane. But after some time, it gets trapped into this vertical resonance. And what you'll see is that essentially it'll be displaced from the plane of the disk, and it goes into this kind of banana or pretzel-shaped type orbit. And so, of course, all of these orbits doing this collectively is what gives rise to the boxy peanut bulge. And you can see this here. So this is now an n-body simulation of an isolated galaxy, of an isolated disk galaxy. And on the top, I'm showing you the surface density distribution face on, and on the bottom, this is shown edge on. And we let it evolve self-consistently with time, and it's going to form bar, spiral arms, etc. And what I'm doing here is I'm rotating the bar to be along the x-axis, and that's because I want you to focus on the bottom panel here. And what you'll see if I fast forward a little bit is that after some time of the evolution of the bar, you have this X shape or peanut shape that pops out of the plane. So I'll go back so you can see that again. So you see it's kind of flat, and then after some time, you have this X or peanut shape-like structure. And this is how these structures form, these boxy peanut bulges. They form through resonances in the disk. Okay, so now that we're on the same page about why bars are interesting and what boxy peanut bulges are, we can go and look at now what we can understand by studying the inner regions of the Milky Way to understand its formation history. So if we want to understand how galaxies form, a good place to go and look is in the inner regions, of course, especially if you want to look at the early formation history, because these inner regions are the first to assemble. Now, in the inner regions of galaxies, we tend to find two different types of structures. On the one hand, we have these so-called classical bulges, which are dispersion-dominated spheroids, which are thought to form through rather violent processes, such as, for example, mergers or also clump migration at high redshift. And on the other hand, you have these other types of structures that we were just talking about, such as boxy peanut bulges. I also mentioned you can also have nuclear disks, and these are all called collectively pseudo-bulges, often in the literature. And the difference for these structures is that they have this secular formation origin. So they form through instabilities in the disks and resonances, or from the bar pushing gas to the center, if we're talking about nuclear disks, but I'll be focusing on boxy peanut bulges for this talk. So these, of course, have very different formation kind of channels, and these different formation processes will, of course, leave very different chemo-dynamical imprints on stellar populations in the inner regions. So by going and modeling the chemo-dynamical properties of the bulge, we can try and decipher the Milky Way's formation history. Now, what we know about the Milky Way bulge in terms of its properties, on the one hand, we know that globally its morphology is consistent with having a boxy peanut bulge. So if you, this is from an image taken from the Near Infrared WISE survey, which can probe, into the inner regions of the galaxy. And if you kind of squint a little bit, you can see that there is this X shape in the inner regions of the Milky Way. And the reason that this X shape is not as prominent as we see in other galaxies has to do with the orientation of the bar. And this is nicely shown in this video here, so in this animation. So this is what a barred galaxy looks like, of course, from the outside, but in the case of the Milky Way, we're in the plane. And also the bar has an angle of about 30 degrees with respect to the galactocentric line of sight. So the peanut is not seen fully on the side, let's say. So the X shape is not as prominent. And in terms of the kinematics of stars in the bulge, what you're seeing here is the line of sight velocity of stars in the bulge as a function of galactic longitude for different heights, for different cuts and different heights above the plane. And what you can see is that at different heights above the plane, the stars rotate quite similarly. And this is called cylindrical rotation. And this is also compatible with what we expect for a boxy peanut bulge. So in terms of the global morphology and kinematics, the bulge of the Milky Way seems quite consistent with being a boxy peanut. However, when we go and look at the chemistry of stars in the bulge, things get a bit more complicated. And that's because when we look at for example, the metallicity of stars in the bulge, and this is from the work of Zoccali et al. In 2008, and this is for a field towards the bulge of the Milky Way called Bade's window, what you can see is that stars have a really broad range of metallicities. From below -1 to supersolar. And this points to the coexistence of multiple stellar populations in the bulge of the Milky Way or in the inner regions. And so the community, there's a general consensus that these metal-rich populations are part of the same population as the disk, which makes up the bar, which makes up the boxy peanut bulge, so that these are all basically a disk-like population. But there's been a bit more of a debate about what the origin of these metal poor stars in the bulge are. So there's been two kind of main scenarios. One scenario is that these metal poor stars that we see in the bulge are part of a dispersion-dominated spheroid, so part of a classical bulge. And in this case, our galaxy would be something like a composite galaxy that has a composite bulge, both a boxy peanut and a classical bulge. And on the other hand, the other hypothesis is that these metal poor stars are just the same population as the thick disk stars that we see at the solar neighborhood, but just continued into the central regions. And this is not just an issue of semantics and how we choose to name these things. The difference here, of course, is that if you say these stars are just part of the thick disk, then that means that you can explain basically everything you see in the inner Milky Way with just disk populations. You don't need any kind of classical bulge or spheroid that formed in a different way in order to explain what we see. So to study this scenario, to study whether the Milky Way bulge can have a pure disk origin, what we did with collaborators in Paris was we went and did some modeling where we modeled the Milky Way with a thin and a thick disk, and we wanted to see if we could reproduce what we see in the bulge with such a model. So to build this, what we did was we used isolated simulations that are really tailored to the Milky Way. And what we did was to take this nice work from Bovy et al. In 2012, who looked at stellar populations in the disk of the Milky Way. And what was plotted here is the vertical scale height of these populations versus the radial scale length. And the color coding is the metallicity. So you can think of each of these as kind of one population. And what was shown really nicely is that you have these metal poor, what you can see really nicely here is that you have this metal poor thick disk population. So it has a large scale height and it has a short scale length. And you have these metal rich populations that are, part of the thin disk and have a longer scale length. So what we did was to build a kind of model of the Milky Way where we discretized this into three populations just to make the modeling easier. And we assigned to our three disks scale lengths and scale heights and kinematics, and also metallicities and alpha abundances that correspond to, let's say, roughly these three big chunks of the disk of the Milky Way. And we gave these masses according to a reconstructed star formation history from the work of Snaith et al., which basically what this said was that these two populations, these thick disk populations that have shorter scale lengths, are as massive as this thin disk population. So 50% of the mass is in these two populations. And so what we did was we constructed this model, an axisymmetric model that has these 3 disk populations, and then we let it evolve self-consistently in isolation. It forms a bar self-consistently, and like I showed you in a previous video, it also forms a boxy peanut. And so then what we do is we go and we observe the bulge of this model, the same way we observe the bulge of the Milky Way with the correct orientation, etc., to see if we can reproduce the properties of the Milky Way bulge with this model. So one of the things we went and explored was to see what predictions these models give in terms of morphology. So in these types of simulations, of course, you know from the beginning which of these particles are in the cold thin disk and which of these are in the hot thick disk. You can tag these. And so what here what I'm showing you is the morphology of these populations at the end after the bar and the boxy peanut has formed. And what you can see, this is shown face on and this is shown edge on now for the cold thin disk population. And what you can see is that the bar is really very prominent in the cold thin disk, and you have this very prominent peanut shape. And in the hot disk population, hot thick disk population, you have a slightly rounder bar and the peanut is less prominent, it's less peanutty. So the fact that this, the cold population has a more barred and peanut-like morphology, it was termed kinematic fractionation, also by Victor de Battista and collaborators that found similar results in that same year. And this is characteristic of disk populations that have different kinematic properties. And why this is happening is that the cold population is losing more angular momentum. So what I'm showing you here is the angular momentum of each of these, of the thin and the thick disk and of the dark matter halo and the total here as a function of time. And what you can see is that the thin disk is losing more angular momentum than the thick disk. And so the bar becomes more elongated in this simulation here. And why is this interesting? Well, we can go back and associate this to what we see in the Milky Way. So if we take these slits along the boxy peanut, which is similar to how we observe the boxy peanut in the Milky Way at these 3 different heights, we can go and look at what we see in terms of the density. So along the axis that I was showing you here, what I'm showing you is the number of stars in the cold thin disk and in the hot thick disk in red. So what you can see is that close to the plane, which is this panel here, you have this single population, this single peak, where basically you're just cutting through the center of the galaxy. Now, as you move further away from the plane, in the cold population, in the cold thin disk, you start to see these 2 peaks. And this is because you're cutting through the 2 lobes of the peanut. Whereas in the thick disk, you only see one peak. And that's because you're not yet, this is because of the fact that the peanut is not so prominent in the hot thick disk population. And as you move even further away from the plane, these 2 peaks become even more prominent in the cold thin disk, and you also start to be able to see them also in the hot thick disk, but you don't see them necessarily at the same, these 2 peaks appearing at the same latitudes or at the same heights. And this is interesting because if we look at the Milky Way and we look at metal-rich and metal-poor populations, which correspond to, let's say, the cold and hot population. So this is the cold population, cold metal-rich population is shown in gray, and the metal-poor hot population is shown in blue. And you look at a proxy for distance along the line of sight. What you can see is that essentially you have this single peak in the 2 populations. And as you move further away from the plane, you start to see this double peak in the metal-rich cold population and a single peak in the metal-poor population. And as you move even further away from the plane, you see this double peak even more prominently in the metal-rich population. And you start to see this peak also in the, you see this peak more prominently in the metal-rich population, and you start to see a peak also in the metal-poor population, this double peak. Of course, there's been a bit of debate about how, statistically significant this double peak is, but you do see something similar also in the Milky Way. So we see similar trends in morphology for a cold and versus hot, or metal-rich versus metal-poor population in the Milky Way bulge, as we see in these models where we have a thin and a thick disk. And if we also go and look at the chemistry now in this kind of model, so now what I'm showing you is a metallicity map for this composite disk model in galactic longitude and latitude. What you can see is that you have these metal-rich parts close to the plane, and you get more metal poor as you move further away from the plane. And if we compare this now with what we see in the data of the Milky Way from apogee, and here I'm showing you the model with the selection function of apogee implemented, you can see that the model reproduces quite well what we see in the data. So we can reproduce all the trends that we see in the data with this kind of model. So I think I'm going to skip forward a couple of slides because I want to, okay, I'll go here. So basically what we showed with these isolated simulations was that we can reproduce the morphology, kinematics, and also the chemistry of the bulge of the Milky Way with such a composite thin and thick disk model. So I had to skip forward a bit because I think I'm going a bit slow with time. But basically, yeah, with these isolated simulations, we could show that the Milky Way bulge is compatible with having this kind of in situ pure disk scenario. But of course, the question that we want to answer is, okay, we can reproduce this scenario with an isolated model of a thin and a thick disk, and things seem to match up. But can we have such a, mostly in situ disk formation scenario for the bulge of the Milky Way in the full ΛCDM cosmological context? Now, to answer this question, what we did was to go and look at the AURIGA simulations. So these are a suite of 30 high-resolution hydrodynamical cosmological zoom-in simulations that have a comprehensive galaxy formation model, and they have masses in the range of the Milky Way. And by redshift 0, they form disk-dominated star-forming galaxies that reproduce a number of the observed scaling relations that we see in local spiral galaxies. And here you can see the evolution of one of these galaxies in terms of dark matter, the gas, and the stellar population here. And you see that by redshift 1 or so, we already have a nice barred spiral galaxy that's formed and is evolving steadily. So what we did was we went and already pre-selected some of the AURIGA galaxies that look the most like the Milky Way bulge, in the sense that they have a boxy peanut at redshift 0. And we went and we studied the chemo-dynamical properties of these galaxies in detail. So what we looked at was the line of sight velocity of stars in the bulges of these galaxies to compare to what we see in the Milky Way. So what I'm showing you here is line of sight velocity and velocity dispersion as a function of galactic longitude. And here I'm showing you first, this is for stars in the bulge of the Milky Way. So I'm separating into 3 different metallicity bins that you can see here. And this is taken from the ARGOS survey. And one thing that you can see that we see in the stellar populations in the bulge of the Milky Way is that the metal poor populations, which are shown in green, have a very similar line of sight velocity to the metal rich populations, which are shown in red, even though these populations, the metal poor ones, are hotter and have a higher velocity dispersion. Now, so what we did was we went and observed the simulated galaxies, these cosmological simulations, in the same way that we observed the Milky Way, and do similar selections, etc. And here we're doing, again, separating into these 3 different metallicity bins. And this is and the lines show you what we see in the simulations. So in this case here, which is the case of AURIGA 18, which is one of the 30 halos we looked at, you see that the metal poor population is rotating quite similar to the metal rich one, not as much as in the Milky Way, but it does seem to be rotating quite similarly, even though it has a higher velocity dispersion. This metal poor population has a higher velocity dispersion. However, if we go and look at another galaxy in our sample, so for example, AURIGA 26, you see that in this case here, the metal poor population is rotating very slowly and very differently from the metal rich population, which is shown in red. So what we found is that the metal poor component has very different properties depending on the galaxy's formation history, which of course makes sense. And here I'm showing you what we found for these 5 halos that we looked at in more detail. And what we did was we went and we looked at now the formation history of the galaxies to try and tie these chemokinematic properties to the formation history. So what I'm showing you here is the star formation rate as a function of look-back time for one of these galaxies, so for AURIGA 18, and you can see the total star formation rate in black. And these lines that I'm showing you on the top here are all the mergers that took place in this galaxy that have a mass higher than 10 to the 7 in solar masses. And the color coding here is given by the ratio, the stellar mass ratio of the merger. So lighter means that it was a minor merger, a smaller merger, and darker means it was a major merger, a more massive merger. And what you can see is that in this case for AURIGA 18, you have kind of few mergers happening after 12 gigayears or so, and the ones that do happen are very low mass. And also for AURIGA 17 here, which is another case where the metal poor population is rotating very similarly to the metal rich one, you see a similar trend. So you have very few mergers happening at late times, and the ones that do happen are very low mass. By contrast, when you look at, for example, AURIGA 26, which I already showed you before, which has this metal poor population that's rotating very slowly, what you see is that it has two very significant mergers that happen after at look-back time less than 12 gigayears. So what this showed us is that for AURIGA bulges to have chemokinematic properties that are consistent with the Milky Way bulge, it seems to be the case that the last major merger needs to take place at quite high redshift, so above 12 gigayears, which corresponds to about redshift of 3.5. And this also places constraints on the mass of any subsequent mergers, for example, in Gaia and Enceladus. Our models and these cosmological simulations seem to suggest that it needs to actually have been a low mass not a low mass merger, but the mass ratio needs to be about 1 to 20, because if you have something very massive coming in at late times, it can penetrate all the way into the central regions of the galaxy, into the bulge, and can disturb essentially the metal poor population that was already formed. So what we did was to quantify the difference between the metal rich and the metal poor population at the end of the bulge for all of the galaxies in the AURIGA sample. And this difference in the metal rich and metal poor population is shown on the y-axis here. And then we quantified here on the x-axis the impact that mergers have had on the galaxy. So what we're doing here is we're summing over all mergers. We're taking the stellar mass ratio of the merger over the redshift at which the merger happens. So if you have a higher stellar mass ratio, of course, it's a more impactful merger. And if it happens at higher redshifts, it won't have as high of an impact on the low metallicity stars. Whereas if it happens at low redshifts, it would have a higher impact on the kinematics of the stars. And what we found is this kind of trend that you see here, in which when you have more mergers that happen at later times, the difference between the metal rich and the metal poor population is higher. So this is where the Milky Way, if you look at the kinematics of stars in the bulge of the Milky Way, this is kind of the range where the Milky Way would lie. And so, of course, if you trust this and you want to extrapolate downwards, what this is telling us is that the Milky Way's formation history must have been very quiescent. So we have one galaxy that kind of matches what we see in the Milky Way in terms of the kinematics, the chemokinematic properties, but really the Milky Way is very quiescent, and it makes up the tail of the distribution of what we see in these simulations. And the other thing that we looked at was the fraction of ex-situ stars or accreted stars in the bulge of these simulations that look the most like the Milky Way. So the ones that are the most like the Milky Way in terms of their chemo-dynamical properties are AURIGA 17 and AURIGA 18. And what you can see is that in these two cases, we have less than 1% of stars in the bulge that are formed ex-situ. So already all of the galaxies with boxy beam bulges in our sample have a low fraction of ex-situ stars, but the ones that have the chemo-dynamical properties that are most similar to the Milky Way have less than 1% of stars formed ex-situ. So this is really showing us that the Milky Way bulge must be essentially an in-situ structure. Now, if we actually want to go and probe the ex-situ fraction if we want to go and probe the ex-situ stars in the bulge, because we want to go and reconstruct the earliest formation history of our galaxy, what these simulations are telling us is that we actually have to go and look at metallicities even lower than -1. If you look at stars that have metallicities below -1, you start to see a more considerable fraction of ex-situ stars for these kinds of very quiescent Milky Way-like galaxies. So if we want to probe this population, we really need to go and probe the lowest metallicities below -1. And the problem with cosmological simulations at these metallicities is that you have very few numbers of actual particles in these simulations, but we're actually running some high-resolution stellar simulations that have a large number of star particles in order to be able to probe these very metal-poor populations in the bulge. So stay tuned for the AURIGA superstars simulations that are coming out soon. So moving on to the next thing that I wanted to tell you about, so on the dark matter content of Milky Way type galaxies. So there's been, of course, we know that there's a strong connection between bars and dark matter, and this has been known for quite a long time. So there's a number of theoretical studies that have shown that bars, the pattern speed of bars will slow down due to dynamical friction when they're embedded in concentrated and live dark matter halos. So dynamical friction was, of course, first kind of developed by Chandrasekhar, and in this formulation, the idea was like, if you have a massive particle that's moving through a sea of homogeneous low mass particles, this massive particle is going to be attracting, as it moves at a constant velocity through these low mass particles, it's going to be attracting particles through gravity behind it, forming a wake. And these particles in turn are going to be pulling on this massive particle, causing it to slow down and lose some kinetic energy. Now, and this was called this was called dynamical friction, or you have this drag force on this massive particle. And this was generalized to spherical systems well, first using the work of Lindenmel and Kalnage, and then Tremaine and Weinberg actually used this to discuss dynamical friction in spherical systems, and in particular also in relation to bars. So what they showed is that also when you have a bar moving through a dark matter halo, you can think of this bar as moving through this kind of you can visualize it as some kind of viscous fluid. So it's experiencing this drag that is making the rotation of this bar slow down with time. So when we have the rotation of so bars rotate with a given pattern speed, and when they rotate, if we go and look at an angular frequency plot versus radius for this galaxy, for this mock galaxy, you have a curve for the stars that looks something like this, right? And for a given pattern speed, let's say this one here, there's a radius at which stars in the disk of the galaxy are co-rotating with the bar. So that means that stars at this radius are going around at the same angular frequency as the bar. And this is called the co-rotation radius. Now, if the bar slows down, if the pattern speed slows down, this radius, the co-rotation radius, is going to move outwards. And so when you have dynamical friction acting on bars, this co-rotation radius can increase. However, the length of the bar is not in theory affected by dynamical friction, only the pattern speed changes. So you can actually go and look at the ratio of this co-rotation radius to the bar length to try and estimate the effect that the dark matter has had on the bar, and if there's been a lot of dynamical friction exerted on the bar or not. And there was already some early works in the late 90s and early 2000s by De Battista and Selwood, who did some experiments, some numerical experiments with this, and they showed that this works quite well. So what they're plotting here is this co-rotation radius versus the bar radius. So this ratio I'm going to be talking about a lot in the next part. And they plotted this versus basically the baryon domination of the galaxy. So if you have this little mock rotation curve, and blue is the disk and green is the dark matter, how baryon dominated, they're basically measuring the velocity, the circular velocity of the disk over the velocity of the halo. And of course, if you increase the contribution of the halo, this ratio here is going to become smaller. So what they showed is that if you have a very baryon-dominated disk, which is the ones on the right here, this ratio of the corrotation radius is quite low. And as you increase the contribution of the halo, this ratio becomes larger. Now, in subsequent works, also by Baptiste and Selwood and also other people like Liathana-Sula, they showed that this is not, as straightforward as this, because here everything else is kept the same. But in barred galaxies, the pattern speed of the bar is also dependent on other things like velocity dispersion and a number of other gas fraction, etc. But this is, to kind of zeroth order. If you do increase the dark matter fraction, you will have this extra dynamical friction acting on the bar and slowing it down. So there was a lot of interest early on to go and measure the pattern speed of bars and to find their corrotation radius and compare this to the bar length in order to see whether bars are fast or slow, and to try and estimate how much dark matter, how much influence dark matter has had on galaxies. And this is often plotted in these kinds of plots here. So here I'm showing the corrotation radius on the y-axis and the bar radius on the x-axis. And these lines here are just kind of heuristically where we call bars slow or fast. So above over here, bars are called slow. So they have this corrotation radius to bar length that's larger than 1.4. And below this line of 1.4, bars are called fast. So they rotate fast, and dynamical friction hasn't had much of an effect on them. So there's been a number of observations that have gone and looked at, tried to measure the bar pattern speed. And I'm showing you here a compilation from Corsini in 2011 and also data from Aguirre et al. In 2015. And this is where you see the observations lie. And there's also more recent measurements from Manga, which find also similar results. So what you can see is that bars in the observed bars seem to be fast. They seem to be rotating quite fast. And this is telling us that it looks like dark matter hasn't had much of an effect on these barred galaxies. Now, of course, to go and study this, properly within, a full kind of ΛCDM context, what you need is, of course, cosmological simulations. Now, there haven't been too many studies that have looked at this in the past, and that's because cosmological simulations in the past had quite a hard time actually producing barred galaxies related to the issue of having very massive bulges. But in the last few years, there's been a few simulations that have been able to form bars, also like the ones I was showing you with AURIGA, that I'll come back to in a minute. So there's been two studies that so far have looked at the pattern speed of bars in cosmological simulations. One is this study from Aguirre et al. In 2017, who looked at the Eagle simulation, and the other one is from Peshken et al. In 2019, who looked at the Illustris simulation. And what both of these found is that basically bars in these simulations have a very large corrotation radius to bar length ratio. So if I very schematically place them on this diagram, they would lie basically somewhere up here. So previous studies of bars in ΛCDM find very slow bars compared to observations. And, there have been kind of some suggestions as why this is happening. Could it be due to low resolution of these simulations? Could it be due to subgrid physics or too concentrated halos? But, the bottom line is these raise the question, are fast bars incompatible or in tension with ΛCDM? Is it that, dark matter halos are too massive in this scenario? And so bars are always going to be slow in this ΛCDM scenario. So before I go on and tell you what we did with the AURIGA simulations, I just wanted to take a very small detour because this is going to be important for what I say later. So quite recently, so in Posti et al. In 2019, they did, Lorenzo did some work using dynamical modeling and using the spark sample of galaxies, for which he could basically determine the halo mass and the stellar mass quite accurately. And so what he did was he plotted this F star here, which is basically the stellar mass over the baryon fraction times the halo mass of these galaxies, so these are these points here, as a function of stellar mass, and compared it with predictions from abundance matching. And this is this gray line shown here. This is what these are what predictions taken by matching stellar mass of galaxies to the halo mass that we see in cosmological simulations. And what Lorenzo found in this work was that in lower mass galaxies, these seem to scatter around the relation. But if you go and look at higher mass spirals, what he found is that it seems that galaxies, if you look at, if you determine everything dynamically, it seems that they have less dark matter. So they're more baryon dominated than what abundance matching predictions are showing, which are these guys here. And he called it the failed feedback problem, in the sense that massive spirals are overly efficient at forming stars, and they therefore lie above the abundance matching relation. And Marasco in 2020 and others in 2020 built upon this work. And these are these galaxies shown in the work of Posti et al., these high mass spirals. And they compared these with cosmological simulations. So these are the high mass spirals in the Eagle simulation, which are shown with this blue points here. And what you can see is that in Eagle, galaxies lie smack on the abundance matching relation. So what this is telling you is that they have these galaxies have lower stellar mass than observed galaxies in similar mass ranges. And so cosmological simulations seem to form fewer stars. So they lie on the abundance matching relation, whereas dynamical studies tell us that these massive spirals need to lie above the abundance matching relation. Okay, so going back now to bars and their pattern speed, what we did was to calculate the pattern speed of bars in the AURIGA cosmological simulations. And to be honest, what I expected to find is that also these bars would be slow and would lie up here, similar to previous simulations. But what we found is that the AURIGA simulations lie actually very close to what we see in the observation. So this is what we found for AURIGA. For some of these galaxies, we were also able to get the pattern speed at high redshifts. And also, so from high redshifts to low redshifts, these bars stay fast in the AURIGA cosmological simulations. And if we compare this ratio of the co-rotation radius to the bar length, you see that AURIGA is compatible with observations, and of course, Eagle and Illustrious have much higher values. So bars in AURIGA are fast, and this is in agreement with observations. So of course, the natural question to ask is, okay, but why are bars in AURIGA faster than in previous cosmological simulations? What's going on there? So we looked at a few things in the paper. I'm just going to show you one of the things we looked at, which is the resolution. So what we did was to say, could the resolution being lower in Eagle and Illustrious than in AURIGA be the culprit for making these bars slower in Eagle and Illustrious? So we reran the AURIGA simulations, but with lower resolution. And what we found is that this didn't change in a significant enough way this value of the co-rotation radius to the bar length. So basically, these points here tagged with 5 are the low resolution runs, and the ones tagged with 4 are the high resolution one. And you see that they become a little bit slower in the low resolution, but nowhere near enough, slow enough to kind of explain what we see in Eagle and Illustrious. And we also went and looked at the gas fraction and also the thickness of the disk. And we found that these were quite similar. And so this probably wasn't what was giving rise to this difference between AURIGA and Eagle and Illustrious. So what we did see that was interesting in AURIGA is that the AURIGA galaxies seem to be much more baryon dominated than in previous cosmological simulations. So again, when I'm going to be talking about baryon dominance, I'm going to be talking about this ratio of, if we look at the circular velocity as a function of radius, I'm going to be talking about the ratio of the stellar component to the dark matter. So what we found in AURIGA is that this ratio is higher at all radii than this ratio in both an Eagle and Illustrious disk galaxies. So the AURIGA galaxies are more baryon dominated than galaxies in Eagle and Illustrious, and this has to do with the difference in star formation and feedback recipes that are in AURIGA compared to previous simulations. What's interesting is now if you go and look at the abundance matching relation, so this is the stellar mass, so this is in the plane of the stellar mass of the galaxy versus halo mass. and the blue line gives you the abundance matching relation. What you can see is that Eagle, which is shown in purple here, lies on the abundance matching relation, as I was showing you before. Illustrious lies slightly above, and AURIGA lies even more above this. So originally, when we ran, when we looked at these simulations and we saw that they lie above the abundance matching relation, we were like, oh, that's not great. Probably they should be closer to the abundance matching relation, but okay, it's not too far off. But what this is telling us, interestingly enough, is that actually you need your galaxies to be above the abundance matching relation if you're going to get the dynamics of the bars right, if you're going to get the internal dynamics of the galaxy right. Because if these do lie on the abundance matching relation like Eagle, then you get bars that are very slow, that are slowed down by dynamical friction in the halo. And also we plotted this in this other plane, which is the stellar mass over the baryon fraction, the halo mass. So this is similar to this other plane, but slightly different. And again, these points here are what you can see from the spark sample from the work of Posti and Marasco that I was showing you. And you can see, of course, that Eagle galaxies, which are shown in purple, lie closer to the abundance matching relation, as well as Illustrious, but the AURIGA galaxies are actually diverging quite a lot from the relation and seem to be following a trend that's similar to what was found for these observed massive spiral galaxies. So the AURIGA galaxies are more efficient at converting gas into stars in some kind of disk-like configuration and are more offset from the abundance matching relation. So what this is telling us is that barred galaxies actually have to lie above the abundance matching relation in order to have dynamical properties that are consistent with observed bars. And so by doing this kind of dynamical studies of the properties of bars in the full ΛCDM context, this can actually help us to try and constrain the subgrid physics that we need to put into star formation and feedback, also at the massive end of the population of spiral galaxies, because these are, of course, massive spirals that we're talking about. Yes, and so with this, I'm going to take you to the end of my talk and just give you some keep home messages. So if you take away just kind of a couple of messages from this talk, the first is that both tailored N-body models and cosmological simulations suggest that the Milky Way bulge has an almost entirely, so over 99% in situ origin. So most of the stars in the bulge of our galaxy were really formed in situ. This is telling us, the cosmological simulations are telling us that the Milky Way has a really uncommonly quiescent merger history. So if we go and find the cosmological simulations that have the chemo-dynamical properties that are the most similar to the Milky Way, these are the galaxies that have a really quiescent merger history. And also this is placing constraints on the mergers that have happened in the last 12 gigayears and tells us that any merger happening between 12 gigayears ago and now needs to have been less than 1 to 20 in order to be able to preserve these highly rotating metal core stars that we see in the bulge of our galaxy. And the second point is that fast bars are not incompatible with ΛCDM, but so we can get fast bars in ΛCDM. But on the other hand, massive spirals do need to be more baryon dominated than what's predicted or what's found from abundance matching, and also what's been done in a lot of hydrodynamical cosmological simulations. So we need to be a bit careful with the star formation and feedback recipes that we're putting in cosmological simulations, because there's a tendency to put more and more powerful feedback. But on the other hand, if we make this feedback too powerful, then you don't form enough stars and your galaxies don't have the right dynamical properties. And I'll leave that there. Thank you.
Thank you very much, Francesca, for this nice talk and also very didactic. I hope all my students are seeing you through the YouTube channel. I'm sure there's a lot of questions. If you have a question, just unmute yourself and speak, or well, maybe raise your hand. I want all of you to talk at the same time.
I have a question, but I don't know if I can be the first one.
Okay, yes, go ahead.
Okay, so.
Go ahead, Santi, yeah.
So thank you.
Go.
Yeah, I can go. Okay. Thank you, Francesca, for the very nice talk. I have several questions, but I will just make a first one now, and maybe later I can make the other ones. This one is basically is a comment and a question at the same time. And it's about this last statement you say that the galaxies must fall above the abundance matching to get the correct relation for the speed of the bars. And I would add that in the current conditions of cosmological simulations that are with limits on the mass resolution, on the spatial resolution, this needs to fall above. But who knows if in the real world this happens, no? The problem here is that with the resolution you have, that is almost hundreds of parsecs, you are not resolving well the orbits of the bar. You are not resolving well the star formation because you basically place big particles instead of an entire stellar population. And because of that, you probably are not resolving well the dynamical friction. So in these simulations in where you have a limited resolution, to create the dynamical friction, to have no as much as dynamical friction as needed to reproduce the velocity of the bars, you need to create more stars in front of the dark matter. But maybe with simulations with infinite resolution, this will not happen. I don't know if you tried to answer these questions, if you are thinking on getting a much higher resolution model in where you can ensure that you're resolving orbits and you can ensure that the things are being done well for the star formation, etc. Sorry for the very long comment.
No, that's a very good comment. So first of all, so two things. The first is on the before I get to the simulations, one thing that I want to remind you is that this is not just what the simulations are saying. So this is what dynamical studies of observed, if we believe the results from POSTI, using the SPARC sample, which is a very well-selected sample, doing very careful kind of dynamical modeling. This kind of trend is what we're seeing also from observed galaxies when we do dynamical studies, that they need to fall above the abundance matching relation. Now, in terms of the resolution issues in the simulations, like I showed you, we were also worried about the resolution. But what we found was that if you take the AURIGA galaxies and you make the resolution worse, you don't get, you don't change in any kind of very significant way. In fact, I was quite surprised that it stayed so consistent, but you don't really change the dynamical friction impacts, how dynamical friction impacts the bar. So you get similar kinds of ratios of co-rotation length to bar length when you go to lower resolutions. About not being able to capture properly resonances and stuff, I mean, these are galaxies that, at least in AURIGA, where we have, over 1 million particles in the disk. So this is kind of very standard, especially, if you think about in the last 30 years, what people have been doing with isolated simulations. 1 million particles in the disk, 20 years ago was considered extremely high resolution. And most of the results that we have, about bars and dynamic friction, etc., are coming from these kinds of resolutions. So I don't think we're not talking about simulations where we have 10,000 particles in the disk. So I do think we have enough particles to see, to start seeing some things. I agree that we, of course, have to be very careful with resolution, especially when we're talking about the formation of the bar, because there we know that noise can play a very important role when you're talking about the formation of the bar. But like I mentioned earlier, we also have these new simulations that we're running, which are called AURIGA superstars, which are basically keeping similar star formation and feedback recipes, but increasing by a lot the number of particles, increasing by 100. So we would have of the order of 100 million particles in the disk. And from preliminary results of looking at these simulations, we find similar results in terms of the pattern speeds of the bars and that kind of thing. So in terms of numerical resolution and particle number, I don't think we have an issue. Now, if we talk about star formation and feedback, of course, I mean, that's a whole different game. And of course, with star formation and feedback, you have to be careful, how you implement things and what you're doing. But the point is here, I'm being agnostic about what kind of star formation and feedback recipes you need to put in, but I'm just saying what the end result needs to be a galaxy that is massive enough. How you get there and what exactly you put in your star formation and feedback recipes is of course very complicated and a different question.
Yep. I just wanted the point in where I am wondering is about the spatial resolution, not the number of particles. Because if you remember in the works of isolated galaxies in where the resolution is worse than tens of parsecs, then you are not capturing the dynamics properly. You can capture the global global properties, but not the very detailed properties. And in cosmological simulations, we never reach it less than 10 parsecs. That's the in where I am wondering.
Yeah. So in the new resolutions, we're also increasing a lot the spatial resolution. So here the softening is of the order of, I think, 300 parsec or something like that. Yeah, if I'm not remembering wrongly. But I mean, again, these. So what could change if you increase the resolution in all of these? You know, if you increase the spatial resolution also in Eagle and Illustris. Oh, and by the way, just to say that when we did with this resolution test with AURIGA, we also made the spatial resolution worse. So we also matched the spatial resolution closer to what we have in Eagle and Illustris. And again, the results didn't change too much. So if you increase the resolution, I mean, the only thing that could happen is that maybe you could increase dynamical friction, but I'm not sure that I've seen any results from any kind of isolated simulations that have shown that by increasing the resolution that you increase dynamical friction. But if you do know them, I'd be really interested in
just to finish it, because I don't want to take all your time. Basically, also increasing a spatial resolution, what you can do is you are resolving better also the shocks with gas, so the gas can fall in the inner parts in an easier way, also generate more clumps, generate more star formation in the inner than in the outer. So at some point it is important, and I understand that putting less resolution, maybe you are not getting big changes, but the big changes can come when you reach a limit on the higher resolution. No? But I understand that it's complicated. I am also doing simulations, so it's just a matter to think for future models.
Yeah, definitely. Mm-hmm.
Pau, go ahead.
Yes. Hi, Francesca. Thank you a lot for a very nice presentation. Maybe you already mentioned it. Maybe I've lost it. But I want to ask you about basically this work by Anke Arensten, where she takes the peaks sample to look at the very, very metal poor population of the bulge.
Yes.
And you know what?
Yes, I know which one.
Okay. So is this evolution, like the loss of rotation and the increase of the velocity dispersion at higher metallicities, consistent with the picture you were showing us?
Yeah, so I mean, so what I was showing you in terms of the bulge is, just bring it back up. So I'm going here, I restricted myself to metallicities of -1. So the -1 is the lowest metallicity I'm looking at. And that was because if I went to lower metallicities in these simulations, I started having a problem with a low number of particles because, of course, these, each particle is like 10 to the 4, 10 to 5 solar masses. And so when you go to these very low metallicities, you just have low, you have Poisson noise, you have low number of particles. But we did find, I'm just trying to see if I have included a plot of the lower metallicity stars also, but I think I haven't. But yeah, so in the appendix of this paper, I have also a plot where we include also stars with metallicities below -1, which is more, I think, where Anke's work and the pig survey was focusing on. And there we found a similar trend in the sense that as you went to lower metallicities, you started to see even less rotation in the simulations that look the most like the Milky Way in AURIGA. So that seemed to be consistent. But to do a more detailed comparison, this is why we're now running these AURIGA superstar simulations, which have a high number of particles, so that we actually have enough particles to go and really look into the lower metallicities below -1. And there, I think it will be really interesting to compare in much more detail to works like that from the pig survey as well. Yeah. But so far, what we're finding is consistent, but we can't say more because we don't have enough particle resolution to really go into lower metallicities even. I don't know if that answers your question.
Yeah, totally. Okay. Thank you. So, I mean, I was just wondering why the trends in her paper look so continuous. I mean, the changes look so continuous that, I mean, I don't know if, I guess it's unlikely that there is a two-component system, but then I was wondering how this gets explained by the formation of a bar and the peanut bulge.
Yeah, so yeah, that's really interesting. If you have some kind of sudden event, or if it's just, kind of transitioning into some kind of halo population, or just, yeah, like the very early hot population in the bulge. So yeah, I think it's going to be really interesting when we have the models that can actually, you can go and probe, all these very metal poor populations and try and trace back what kind of accretion events and the merger history at really early times is. But yeah, it does exactly in the Milky Way, it does seem to be a very kind of continuous, smooth transition, where I think you just have stuff, that was hot, that formed really early on from some kind of very early mergers, but then you just didn't have any big merger happening at later times from 12 gigayears onwards that really disturbed the center of the Milky Way. You can disturb, of course, the outer parts of the Milky Way, and we see a lot of these things happening, but in the center, really in the bulge, it seems like you had something hot that then just kind of progressively cooled down to form the thinner and thinner disk, and then the bulge, formed from the bar, basically from these vertical resonances, and you don't have much of this, something very hot spheroidal component, let's say. This is at least how I interpret the things that we see.
Okay. Yeah, thanks. Makes sense. Thank you.
Thanks.
Francesca, one quick question. When you say the galaxies in AURIGA are more baryon dominated, you really are comparing with the stars, so the stellar dominated. How do you check the gas content in that galaxy, and how does it compare with the illustrious?
Yes. So yes, I think for this one I do have a plot in my extra slides somewhere. Yes. So this is showing you the gas, the gas density over the stellar density as a function of radius for the different simulations, and what you can see is that especially in the outer parts here, AURIGA and Illustrious are similarly a bit more gas-rich than Eagle. Mm-hmm. But in the case of, so what's interesting for us here is actually looking at the gas density inside the corrotation radius, because that's where we think this is going to be playing a role for the bar. And because the bars in Eagle and Illustrious are so slow, the corrotation radius is much larger. And the bar length is also larger. So if you normalize the radius to the bar length, then what you see is that the gas content is quite similar in Eagle and AURIGA, and it seems to be a little bit higher in Illustrious. So yeah, the gas content might also be playing some kind of role, but we didn't find evidence that, for example, what we would expect if gas was important would be that AURIGA would be much more gas dominated than the other ones, but that doesn't seem to be the case, especially if we look inside the bar radius.
It's interesting. You want to now that another question to me, but I have a lot of questions, so I maybe talk to you later. But just when you calculate the stellar mass, you calculate total stellar mass, I guess.
In this case here, yeah, I think I was looking, if I remember correctly, inside 25 kpc, stellar mass inside 25 kpc radius.
Okay.
Yeah.
No, because I was wondering if you compare the mass inside the corrotation radius that you are doing here with the gas and outside, I was wondering, over the fractions.
No, for the stellar mass, it's taking into account the whole galaxy, the disk of the galaxy. Yeah.
Okay. And when now you show me this, so illustrious simulation have more stars versus dark matter, you want to put it like that, than AURIGA, but also have more gas. Is that only inside, or is it, how come the difference? If the star formation is more efficient in Illustrious than in AURIGA, why do they have more gas?
So the star formation is the most, it's, let's say, most efficient in AURIGA from the three.
Yeah.
And yeah, I mean, this is, I didn't go into that much detail to look at exactly, because of course it depends a lot on how the feedback is implemented. I mean, are you consuming the gas, or so you have, you know, higher star formation efficiencies like in AURIGA, or are you just ejecting it? Yeah. So in illustrious, So in illustrious, the AGN feedback, for example, was more aggressive than in AURIGA, and so maybe that's also what's creating this difference. Also in EAGLE, it's the feedback, both the stellar and the AGN feedback, is much more bursty than in AURIGA. So maybe that also is kicking out more gas, and you're more gas poor at the end. Yeah.
Okay, thank you. A quick one, sorry, Armando, I didn't see you, but a quick one for Armando. Well, in your simulations, I mean, all the classical models are a consequence of an interaction, no, with another gas, right?
Sorry, in the AURIGA simulations, you mean?
All the classical models, if you want to put it like that, are a consequence of an accretion, no, or an interaction with another galaxy. Otherwise, yeah, is that? I mean, I guess you selected a type of galaxies that are similar to the Milky Way, with the morphological characteristics, etc. What happened? I don't know if you check it or if there's some publications. But what happened in galaxies, for example, with a larger bulge to this radio? Is that still true, or? So
you mean for the bulges?
Yeah, for the bulges. I mean, can you have classical bulges from in a different way, or are always a consequence of an interaction with another galaxy?
So in AURIGA, because of the ISM model and how smooth it is, and you don't have any kinds of, you don't have any cold clumps or any kind of thing like that, because of the way the ISM model is. So yeah, any kind of classical bulges that you would have in AURIGA would be the consequence of basically mergers, essentially.
Okay.
But yeah, of course, as Santi was saying, in that case, when you're looking, you know, especially if you want to look at formation of clumps from a cold gas, then you need to change, of course, your ISM model and your star formation and feedback model. Yeah.
Well, the question is if the proportions of, I don't know if AURIGA now have like a, I don't know, the volumes of AURIGA simulations, like the resolution. But if they get the proportions of different morphological types right or not.
So AURIGA are zoom simulations. So they're zoom simulations that are picked to be kind of similar to in mass to the Milky Way, and they have a certain isolation criteria. So it's not really a representative sample of all of the population.
Right.
So for that you need something more like TNG or TNG 50.
Yeah. Thank you. Armando, can I ask you a question?
Hello, Francesca.
Hola, Armando.
Hola.
Good.
So I have just a couple of questions. Thank you very much, by the way. I learned a lot. So
I hear you from very far away. Can you just get closer to the speaker?
How about now?
Better.
I have a cold, so that might be
better. Yeah.
Okay.
A regular cold, by the way. Okay, so just two things. Thanks again. One thing is that regarding the subgrid physics that you have been talking already, and Patricia and Santi. So if the AURIGA model does better for the bar galaxies, could be the subgrid physics something that is being done better at the scale where the bar or the star formation associated with the bar could play a role? Because you were mentioning feedback, but feedback in principle it will be present in both types of galaxies, right? I mean, you could have an AGN in both kinds. But if you will have something in your recipe in AURIGA that makes the subgrid physics for the formation of a star in bar galaxies better than the other, could that explain it? And the other thing related with that is that usually in these things that you actually cannot have so many parameters in the feedback, or you have more or less the same parameters in all simulations. If you do better in one type of galaxy, you usually do worse in some other kind of galaxies. So is that the case? And the last part is, now that you know that the mergers have an impact, or it's a different part of your talk. And now that you have you know that the mergers have an impact on how is the distribution of the less metal poor stars in your pseudo bulges, or your peanut classical, the peanut shaped bulges. Can you do other type of simulation that are not so consuming or so demanding in terms of computing time to actually explore other things, not just simply the whether you have a major merger or not. For example, the orbit of the major merger, or how is the host galaxy, for example. Thank you.
Yeah, okay, let me try and see if I remember them. So the first one was if the star formation and feedback recipes are in such a way that they are affecting only the bar region. Was that the...
Yeah, the star formation in the bar region. So it boosts the star formation as a cause or due to the presence of the bar only.
So I would say no, because of course these are cosmological simulations. So you're starting really, from redshift, I don't know, 127 or something, and you're really modeling the whole formation of the galaxy. So you're going, you have your your little proto galaxies that are forming and merging and all that stuff. So it's not that necessarily that it's the feedback at late times that is different. It's really, that the way that you've implemented the feedback, it, let's say, allows, from early times, the galaxy the star formation to happen in such a way that you get in the end this kind of massive disk galaxies. So I wouldn't say that it's something to do with feedback necessarily at late times. I think it has to do more with just how the feedback is implemented, because of course, in all of these cosmological simulations, you're not resolving you're resolving just stellar populations, and you don't resolve any of their supernova. So you need to kind of, everyone does it differently in how they try to mitigate the problems with resolution and try to get enough feedback to actually stop the collapse of everything and forming a huge bulge basically at the end. So people have been, using feedback to remove, the low angular momentum gas and then reaccrete it again and get more like disk-like galaxies. But the problem is that I think at some point we need to be careful to not overstep and make the feedback so strong that in the end you're also not forming enough of a disk as well. So I would say that it's not something to do with late time feedback, but it's just in general how the stellar feedback and how the AGN feedback is implemented, which is a bit different in these three simulations in general. Yeah, I mean, we haven't gone into yet a detailed exploration of exactly trying to figure out exactly what we think is the thing that worked best, because of course also in AURIGA, I mean, the feedback is a huge approximation, right? I mean, we know this is not how feedback happens, so, from stars and AGN. So it's, what it's telling, it depends what kind of question you want to ask, right? And what kind of question you want to answer. But basically it's telling you something about not making the overall feedback too powerful, I think, which is important in order to get the dynamics correct. And then the other question was, I forgot the second one.
Whether since it works better for bar galaxies, whether it works worse for other kind of galaxies.
Other things.
Or it's perfect.
AURIGA is perfect. No, of course there are things that don't work well. Always, you're right. To be honest, I'm not really sure where. I'm not really sure where the problems are in AURIGA. I'm sure there are. Because AURIGA are Zoom simulations, there's not been the same kind of studies that have been done for Eagle and Illustrious, which are really, full population of galaxies, and you can look at a lot of different things and do a lot of statistics. So I don't think we have, I'm sure it probably doesn't do well somewhere, but we don't have the same kind of studies because of the fact that these are Zoom simulations. And so you're really selecting a subpopulation of galaxies you want to resimulate at higher resolution. So the statistic, it wouldn't be a fair comparison because the statistics are the same. But I don't know anything where they go really badly, but I'm sure there might be somewhere. But of course, that's the game, right? You want to try and, like you say, if you nudge something in one way, you nudge it in the other way, and then the game is to try and get everything to work, right? And that can tell you something. And then the last question was about bulges and if we're trying to use different types of simulations. Yeah, I think so. The different types of simulations that we're trying to use is I mentioned is the ones that have higher particle number. you keep all the physics the same, you just increase the particle number, and these are relatively cheap in a certain sense to run. So it's like AURIGA, but just more particles. And then for this, exactly what we want to do is we want to go and look at, at these, try and look at earlier accretion and merger events. Now, if you're interested in one particular merger event like Gaia Enceladus, for example, then of course, yeah, you could do something different, like take some two galaxies that have the properties you think the Milky Way had and your Gaia Enceladus had at that time, and try different orbital orientations. Of course, in the cosmological simulations, you get what you get. You can't force it, right? But no, we're not running at the moment.
For example, you cannot avoid the hydrodynamical part. Like say, okay, let's do that only with stellar and dark matter particles to see what happens.
You could. It depends on the question you want to ask. I mean, I think like always, these are numerical experiments, and it depends what kind of questions you want to answer. And for some things, you need the hydrodynamics, let's say, because of the question. If you want to answer questions about continuous star formation, of course, you need to have gas so you can form your stars. Yeah. But if you're interested, in just the stellar dynamics, then you can. Then you don't necessarily need the hydro.
I mean, I say so because it's a pity you only have 7 or galaxies or so, because you certainly could explore more things like other secondary parameters, and maybe you can relax your complete modeling just to explore that. You are able to, because at the end it's mostly stellar, right?
Yeah. No, definitely. If you give me more computational time and some student, I'm happy to do it.
Look at my cell phone.
Yeah.
No, I don't have. Well, I don't know, Santi. Maybe he's the computing guy. Okay, thank you, Francesca.
Thank you, Armando.
Okay, is there any other question for Francesca in the audience? Well, then I would like to thank you again, Francesca, for this very nice talk. One quick final question: once they form, bars survive in AURIGA simulations, or they can destroy? They can be destroyed.
No, they survive. So we don't have any destructing bars unless you have some kind of huge major merger or something like that. But the bars, in AURIGA are definitely they're long lived, and we see them forming from redshifts of like 1.5 to depending on the case, but they form from quite early on. High redshifts, and they survive. Yeah.
Okay, cool.
Yeah.
Well, then now, yes. Thank you again for the very nice talk.
Thank you for the invitation.
Well, see you soon.
Yeah, hopefully I can visit you soon.
Hopefully next time we can invite you to Madrid. Yeah.
That would be great.
Okay. Well, thank you to all for joining. Next seminar, we have another IPARCOS colloquium on Friday, I think. Otherwise, next seminar is, I think it's also next Wednesday at 5, but I don't have the list in front of me now. So sorry. Well, thank you to everyone for joining. See you next week. Bye.
Bye. Thanks.
Bye.
Bye.
Ciao.
Chao. Saludos a Amy.